Good morning, students. In yesterday's class, we derived this equation for shear stress in the beam while it is bending. Tau is equal to Fe into Ay bar by B into I. This is the shear stress formula, in which the tau is the shear stress in the beam at a particular layer EF. F is the shear force across the section. Ay bar is the first moment of area about neutral axis, the area which is above the EF level. I is the moment of inertia, whole section about neutral axis. B is the breadth of the layer EF, which may vary or constant along the beam, across the beam. I hope you understand how to derive this formula in yesterday's class. By using this formula, we can solve the problems for different types of sections to calculate the shear stresses across the section. In this whole chapter, this formula is very important for calculating the shear stress. Okay. In this class, we derived the equations for the different basic sections by using this formula. Variation of shear stresses across standard beams or standard sections. Let us take the first standard section is a rectangular section. Consider a rectangular section of width B is the width and depth is the D. Let EF is the one of the section we are considering. This is the EF section, which is at a distance of Y from the neutral axis. This is the neutral axis. We are considering EF section at a distance of Y, at which we are going to calculate the shear stress due to the sliding of the area above EF level. This is the shaded area. Due to sliding of this shaded area, due to the unbalanced force acting on this shaded area, the shear stresses will be developed at the EF level. So by using that formula, shear stress formula, we can calculate the shear stress at a distance of Y. So shear stress in terms of Y. By varying the Y, the shear stress is also varies at the extreme layers and at the neutral axis. This is the distribution, shear stress distribution across the section. That means the shear stress at the extreme layers are 0 and the shear stress at the neutral axis is maximum. The shear stress varies across the section as parabolic variation, like this. How to get this diagram, shear stress distribution diagram? After deriving the equation for the shear stress across the cross section, we can say that the shear stress varies across the section as parabolic variation. And the shear stress is maximum at the neutral axis, which is equal to 1.5 times the average shear stress. Tau max is equal to 1.5 times the average shear stress. How to get this formula? Let us derive. Let EF be the layer at a distance of Y from the neutral axis. Let the shear force, let the shear force on the section be F, the total section subjected to shear force F, which is the one of the section on the beam. A rectangular section having the breadth B and depth D. That is the D by 2 from the neutral axis extreme layers distances. Let us take the Y. Let us take a one layer EF at a distance of Y. Shear stress at the section EF is at particular section or particular layer, the shear stress formula tau is equal to F bar by B into I. Just earlier I said that in the earlier class we derived that formula F bar by B into I, where Ay bar is the moment of area, which is shaded area here, moment of area above the section about the neutral axis. First moment of this area about neutral axis is called the AY bar, which is denoted by AY bar. In this, what is the AY bar? What is the A area of the shaded portion? Why we are taking AY bar area of the shaded portion? Because we are going to calculate the shear stress at particular level EF. When we are calculating the shear stress at particular level EF, we should consider the area above the level EF. Just earlier class I said that, let us take, this is the rectangular section, this is the EF, then by sliding the area above the EF level, this is the area above the EF level, shaded area, by the unbalanced force dm by I into y into dA, dm by I into y into dA is the unbalanced force. This due to unbalanced force, the portion or the area which is above the level EF, which is slides over the another area. Due to this sliding of the one area over the another area, the shear stresses will be developed at the level EF. Here the shear stresses will be developed. So to calculate the shear stresses at EF level, we should consider the area above the level EF. Okay, students? So that is area. In AY bar, area is this much area. How much this area, shaded area? The shaded area is d by 2 is the total height from the neutral axis. From that we can subtract, if we subtract the y distance, then we can get the height of the shaded area. Then what is the breadth of the shaded area? Breadth of the shaded area is B itself. Therefore, area is small a or capital A. We can use whatever it is, small a, capital A. Area of that shaded portion is B into breadth into height. Height of the shaded portion is d by 2 minus y. D by 2 minus y. So this is the area in terms of y. Area in terms of y. If y equal to 0, if y equal to 0 means we are considering EF level at the neutral axis. When we are considering the, whenever we considering the that layer EF at neutral axis, we should consider all the area which is above the neutral axis. All the area which is above the neutral axis is d by 2 into b. So whenever y is equal to 0, b into d by 2 is the area. Okay, students? If y is equal to d by 2, y is equal to d by 2 means we are considering the level, that is the layer EF at the extreme upper layer. Y is equal to d by 2 means y becomes d by 2 means the layer which is considering at the extreme upper layer. When y is equal to d by 2 minus d by 2 is 0. Therefore, area which is above the level EF is 0. There is no another area which is above the level EF. Therefore, area is 0. Like that, the area at which we are going to calculate the shear stress, we should consider the area above that layer. Okay. So what is the area now? B into d by 2 minus y. And what is the y bar means? Y bar is the center of gravity of this area. Center of gravity of this area from the neutral axis. Combinedly we can call it as AY bar, combinedly call it as first moment of the shaded area about neutral axis. Okay, first moment of area into whatever we consider the area into distance of its CG from neutral axis is the first moment of area about neutral axis. So what is this distance? Y bar means this is the distance of CG from the neutral axis. How much distance? This height is d by 2 minus y. This height is d by 2 minus y. So where the CG is located? from this topmost position or from bottom portion EF level, from the EF level, the CG which is located at a distance of half of the d by 2 minus y. Total height is d by 2 minus y. This the CG is located at the center because it is a rectangular in shape. Therefore, it is half of the d by 2 minus y is the distance from EF to CG. Then remaining distance is y. So y plus half into d by 2 minus y is the y bar. Understand, students? Can I explain once again how to take the y bar? Y bar is the center of gravity, the center of gravity of that shaded portion from neutral axis. This is the y bar distance. So how to get this y bar means from neutral axis to EF level is y. This is the y distance. And remaining distance, this distance, that means the distance of EF level, EF layer from the center of gravity of shaded portion. So shaded portion center of gravity from the EF level is half of the total height, half of the total height of the area. Total height of the area is d by 2 minus 1. In that, half into d by 2 minus y is the remaining distance. Therefore, total distance is y plus half into d by 2 minus y. So from this, y plus 1 d by 4 minus y by 2. So y minus y by 2, y by 2. So y by 2 plus d by 4. This is the y bar value. If 1 by 2 remains constant, that is the common, d by 2 plus y. Dear students, ఇందులోకి వెళ్ళి 2 కామన్ తీస్తే డినామినేటర్ లో ఒక కామన్ తీస్తే ఇక్కడ y ఇక్కడ d by 2 plus y. This is the y bar value. Dear students, area value is equal to how much area? b into d by 2 minus y. This is the a value, this is the y bar value. Therefore, a y bar in this formula is b into d by 2 minus y into 1 by 2 d by 2 plus y. It is d by 2 minus y, d by 2 plus y. So a minus b into a plus b. Therefore, b by 2 into d square by 4 minus y square. Let us go to the next line. So b into d by 2 minus y is the area. Y bar is the y plus half into d by 2 minus y, half into d by 2 plus y. Therefore, a y bar is equal to b into d by 2 minus y into half into d by 2 plus y. Therefore, b by 2 into d square by 4 minus y square. This is the a minus b into a plus b form. So a square minus b square. D square by 4 minus y square. This is the a y bar value. Keep it aside. Then find the moment of inertia. What is the moment of inertia of this rectangular section about neutral axis? We know that the basic formula is b dq by 12. This is the moment of inertia, b dq by 12 of 1 by 12 into b dq. Then substitute this ay bar and I value into our shear stress formula. Our shear stress formula is F into ay bar by b into I. What is the b here? Denominator in this b is the breadth of the level EF. Here the breadth of the level EF is equal to the breadth of the whole section. Breadth of the whole section. In some other case, these two are not equal. Breadth of the EF level is not equal to breadth of the rectangular section. It is not equal in case of triangular section. In case of triangular section, because triangle is varies from base to apex. If we consider the level EF somewhere else, the breadth of the EF level is not equal to the breadth of the whole section, isn't it? Let us consider this is a B, this is not the B. So in this formula, shear stress formula, this B is represents always the breadth of the EF level. This total equation is related to the EF layer. The layer EF which is considered at a distance of y from the neutral axis. This is not considered for the whole section. This is considered only for a level EF. Dear students, So in this, by substituting f into ay bar, ay bar value is b by 2 into d square by 4 minus y square divided by b as it is, because here b is the breadth of the level ef, which is also equal to breadth of the rectangular section in this case. B into I is the BDQ by 12. Upon substitution of all the parameters into equation, we get 6F. The 12 is goes into the numerator. 12 by 6 is the 6. 12 by 2 is the 6. 6F, BB is cancelled, and remaining it is BD cube. So 6F by BD cube into D square by 4 minus Y square is the formula. This formula, which represents the shear stress formula in the rectangular section at particular level y, at a particular distance of y from the neutral axis. That means shear stress varies with respect to y. If y varies, the shear stresses also varies. In this formula, by looking this formula, we can say that by increasing the y value, the shear stress value decreases. If the decrease in y value, shear stress increases. So this shows the shear stress variation varies parabolically, because shear stress too is varies along with the y square. Based on the y square, therefore the shear stress varies across the section parabolically. And let us look where the shear stress, how to calculate the shear stress at different levels of y, at different distances of y. If we consider the y is d by 2, whenever the y d by 2, if y becomes d by 2, whenever the level EF layer is considered as extreme top layer or extreme bottom layer. Therefore, if we substitute the y equal to plus or minus d by 2, plus or minus means y considered in this direction plus, in this direction minus. So y is d by 2 means at this level. Y is minus d by 2 means at this level. So at these two portions, if we substitute y is equal to d by 2, therefore d by 2 whole square, d square by 4. D square by 4 minus d square by 4 is the 0. Therefore shear stress value is 0 whenever we substitute the y is equal to d by 2 or minus d by 2. Therefore shear stresses are at extreme layers are 0. At this point, shear stresses are 0. By drawing a vertical line across the section, the shear stress values on the vertical line will be represented as 0. Here the 0 shear stresses. Clear, students? So where it is maximum, if we want to get the maximum shear stress from this formula, we can we should first differentiate this equation with respect to y and equate to 0. Then we can get the maximum shear stress distance from the neutral axis. So differentiate this equation with respect to y. Differentiation of this equation with respect to y, 6f by bd cube is the constant. Differentiation of d square by 4 is 0 minus 2y. Y square differentiation is minus 2y. So 6f by bd cube minus 2y equal to 0. Then equal to 0, then y equal to how much? Y becomes 0. Y becomes 0. So at y is equal to 0, whenever the y 0, the shear stress is maximum. So by substituting the at y plus 0, we can get the maximum shear stress. Therefore, maximum tau equal to 6f by bd cube into d square by 4. This value is 0. 6f by bd cube into d square by 4 is the maximum shear stress whenever the y is equal to 0. Okay? Y0, where the Y0? Y0, whenever we consider the level EF or layer EF at neutral axis. If we consider the new layer EF at neutral axis, y becomes 0. Okay, the area which is considered above neutral axis, then the level EF is at neutral axis, therefore y becomes 0. So whenever the y becomes 0, the shear stress is maximum. The shear stress which is maximum, that value is 6f by bd cube into d square by 4. In this 6f by d square and d would cancel, the bd remains in the denominator. So 6 by 4 is the 1.5 into f by bd. F by BD is called the average shear stress because shear force divided by area. B into D is the area of the cross section. Shear force by shear area is the average shear stress. So this is represents toe average is equal to F by D average shear stress. Therefore, toe max is equal to 1.5 times the average shear stress I represent in the diagram here. Toe max is equal to 1.5 times the toe average. Toe maximum is equal to. So maximum shear stress will be developed at what distance? At neutral axis. Clear, students? At y is equal to 0 means at neutral axis the maximum shear stress will be developed. The shear stress varies across the section by locating the 0 at this place. First, to draw the vertical line across the section, locate the points on the vertical line. It represents the shear stress value 0 at the extreme layers, and shear stress is maximum at neutral axis. By drawing the axis at neutral axis, extend the line, locate that horizontal line, the toe maximum, it is 1.5 times the toe average. By joining these 3 points by parabolical curve, we can get the shear stress distribution. Why it is called the parabolical curve? Why not it straight lines like this? Because the shear stress varies across the section or along the based on the y, which is y square. Shear stress varies based on the y square. That's why it becomes a parabolic curve. Here the formula we get that shear stress is depends on the y square. Therefore, it's a parabolical curve. Clear, students? So thus in rectangular section, maximum shear stress is at neutral axis and it is 1.5 times the average shear stress. It varies parabolically from 0 at extreme fibers to maximum at mid depth as shown in figure B. In figure B, this is the shear stress distribution across the section. Clear, students? So as earlier we studied in the bending stresses chapter, the maximum bending stress will be occurs at the extreme layers and 0 bending stress is at neutral layer, isn't it? We drawn the shear stress bending stress distribution like this by drawing the vertical line. This is the compression and expansion. Sorry, it's compression and compressive forces here and tensile forces will be developed here. Like this, we drawn the shear bending stresses at neutral axis is 0. The bending stresses at extreme layers are maximum. But in case of shear stress, the shear stress at extreme layers are 0 and shear stress at neutral axis is maximum. Simply opposite to the bending stress distribution. Clear, students? The shear stress at extreme layers are 0 because if we consider the EF level at extreme layers, it doesn't have any area above the level. If there is no area, AY bar is 0. AY bar 0, then shear stress 0. If AY bar is 0, shear stress is 0. Even if we apply the shear force, even if we have the breadth of the layer at extreme layer and I value, AY bar is 0. If AY bar 0, shear stress is 0. So if we consider the EF level at this level, we doesn't have any area above the level EF. If there is no area, there is no sliding part above the level EF, then shear stress is 0. Similarly at the bottom. So if we consider the EF layer at this layer, bottom, extreme bottom layer, which doesn't have any area below the level EF. If there is no area, there is no sliding part at the EF. If the sliding part is doesn't have any sliding part, then shear stresses are 0. Like that, shear stresses at extreme layers are 0. Shear stresses at neutral axis. At neutral axis is maximum because if we consider the EF level at the neutral axis, we should consider this is total area of the total section area, of the section area. So of the section area will be slides on the EF layer. Therefore, total of the area will be slide the neutral layer. Then maximum shear stress will be developed at the neutral axis or neutral layer. Okay, students, this is the variation of shear stress across the rectangular section. Similarly, we can derive for different basic sections. Another basic sections. Let us look. Another basic section is circular section. Circular section. So consider the circular section of radius r. This is the circular section of the beam having the radius capital R, OE. Let EF again. Let us consider EF layer. EF be the layer at a distance of y from the neutral axis. For the circular section, the neutral axis which is passing through the center. Okay. From the neutral axis, we are going to consider a layer on which the shear stresses are to be calculated. That layer is at a distance of y from the neutral axis. The distance of y from the neutral axis. Clear, students? Let the shear force on the section is F again. The shear force will be developed on this section is taken as capital F. What is shear force? Every time I'm telling shear force. Already we studied in the shear force bending moment chapter. For example, let us consider what is this? It is a cantilever beam. By applying the load at the free end W, the shear forces are varies along the beam. What is the shear force at this point is W. The shear force is remain same across the beam, along the beam. So shear force diagram on rotation. This is the baseline. Shear force is downwards is positive W, and which is constant throughout the beam, and it looks like a rectangle. This is a positive shear force. The shear force along the beam is constant, which is equal to W. Here the shear force is F. We are taking shear force along the beam is taken as F. So for this beam, let us cut the beam at the particular section. We looks from side view. This is if it is a rectangular section like this. Okay. If the cut at particular section, we looks a rectangular section. If it is circular section beam, if it is a circular section beam, it looks like a circle. If you cut the particular section in the side view, it looks like a circle like this. So in this circle, this is the neutral axis. This is the neutral layer. This is the neutral axis. Let us draw neatly. If this is cantilever beam, this is the cantilever beam. If we cut at a particular section, it looks like a circular section like this. This is the neutral layer, and the intersection of neutral layer with the cross section is neutral axis. Okay, this is the neutral axis. So we are considering EF layer at this particular layer. We are going to consider we are going to calculate the shear stress at a distance of y. That why we are considering the layer, because how the shear stress varies with respect to y. If we know the shear stress variation with respect to y, we should consider the layer at a distance of y and find the shear stress equation at that particular level here. Then we can say that the shear stress varies across the y. Okay, like this. Consider a circular section having the radius capital R and the y distance at a distance of y. Consider draw a EF layer above which the shaded portion, due to this shaded portion, the shear stresses will be developed at the level EF. Okay, whatever the level we are considering at which the shear stresses will be induced in the beam due to the area above or below which. Okay, మనం ఏదైతే లేయర్ కన్సిడర్ చేస్తున్నామో ఆ లేయర్ కి పైన ఉండే ఏరియా వల్ల కానీ ఆ లేయర్ కింద ఉండే లేయర్ వల్ల ఏరియా వల్ల కానీ ఆ లేయర్ దగ్గర షియర్ స్ట్రెసెస్ డెవలప్ అవుతాయి. ఫర్ ఎగ్జాంపుల్ మనం కన్సిడర్ చేసిన సర్క్యులర్ సెక్షన్ ఇది, లేయర్ EF ఇక్కడ. If the layer EF will be slides, that is the area which is above or below that layer EF slides over that EF level, then shear stresses will be induced. For example, after sliding that areas at EF level like this. If we slide at the particular layer in this direction or in this direction below area, the sliding action will be takes place at a particular layer. Due to the sliding action, the shear stresses will be induced here. Shear stresses will be induced parallel to apply load. Okay. So that layer, in that layer, shear stress formula is this one. Shear stress at a section EF is tau equal to, again, we derived this equation already, FEAY bar by B into I. Tau equal to FEAY bar by B into I. By applying this formula at the level EF, then we can get the shear stress variation across the circular section. It is also parabolically varies. I shown in figure B here. Shear stresses are 0 at extreme layers and shear stress is maximum at particular neutral axis. Shear stress is maximum, tau maximum, and tau is the shear stress at particular level EF. This is the tau. So let us look the parameters which contains in the shear stress formula, F AY bar into by B into I. So F is the shear force across the section, which is constant across the section, and B is the breadth of the EF level, that is EF layer, which is not constant here. If we consider the EF layer at neutral axis, the breadth becomes diameter of the circular section. So B is not constant here. I is the moment of inertia across the section, moment of inertia of the section about neutral axis, which is also constant. So Fi are the constant. Our variables are area, Y bar, and B. A is the area above the level EF. If we consider the level EF at the neutral axis, the area becomes half of the circle. Y bar means the area, that is the center of gravity of that shaded area from the neutral axis. That is the Y bar distance always. Wherever we consider the EF level, above which the area, we should consider the area. For that area, center of gravity of that area from the neutral axis is represented by Y bar. And B is the breadth of the level EF, breadth of the layer EF, level or layer EF. Dear students, let us go for detailed derivation. In that formula, where AY bar is the moment of shaded area about neutral axis. I is the moment of inertia about neutral axis. B is the breadth or width of the section EF at Y distance from neutral axis. So B is varies with respect to Y here. B is also varies with respect to Y. B becomes B is depends on the Y. So consider a strip of thickness dy at a distance of y. Why we consider the strip here? This area which is above the layer EF is not a symmetric area as in previous case in rectangular section, because in rectangular section, that is the shaded portion is rectangle itself. We can calculate the area of that shaded portion in the rectangular section beam easily. Dear students, here the shaded portion is rectangle. We can calculate easily the area, but here we cannot calculate directly the area above the layer EF. Okay, that's why we are going to consider a small strip here, a small strip. This is the thickness of the strip is dy, because that area which is considered at distance of y from the neutral axis, let us take the dy is the thickness of the small strip. This is. So whenever the area is unsymmetric, we can calculate the, we can assume the small area. By integrating that area, we can get the total whole area. So to get the area above the layer EF, we should consider a small strip of thickness dy at a distance of y. Clear, students? So if you want to find the total area above the level EF, by finding the area of this strip and integrate the area of this strip, then we can get the total area above the level EF. So what is the area of that small strip now? this total length into dy is the area. Total length, how much? It is EF. EF is the total length into dy is the thickness. This is the area of the small strip. Here students, area of the small strip. And y is the distance. Y is the area of this distance. See, center of gravity, the small area is y itself, because it is we consider a small area which is at a distance of y. Center of gravity of the small area is also at a distance of y. So EF into dy is the area. A into y is the first moment of area of the small area. First moment of area. Okay, students. So first moment of area ni manam find chestunna small area ki. If we integrate this one from y to y varies from y to when we consider the strip at this place, is the distance of that strip is y. When we consider the strip at this place, y becomes capital R. So y varies from y to r. EF into dy into y is the first moment of area. First moment of area of whole section, whole area is integration of y to r, EF into dy into y. So what is the EF? This what is the length of the EF? We should know the length of the EF. EF is equal to from the diagram, from the circular section diagram, we can write as EF is equal to EB. B is the center point of EF. 2 times EB, isn't it? Because both are equal, EB equal to FB. So 2 times EB, we can write it as 2 times EB. EB is the distance from E point to B point, and distance from B point to F point is also same. Therefore, EBF equal to 2 times EB. So how to get the EB distance? By taking this right angle triangle. By taking this right angle triangle, EB is equal to, or EB is equal to square root of r square minus OB square. OB square is the y. So therefore, square root of r square minus y square is the EB. Otherwise, EB square is equal to, in right angle triangle, one of the side square is equal to hypotenuse square, that is the hypotenuse in the triangle is r square, EO, minus another side square is y square, BO square or y square. So EB can be write as, if we want to write the EB is equal to square root of, are you understanding the students? This is the totally mathematical equation. The EB is equal to r square minus y square. Therefore, EF total distance is 2 into r square root of r square minus y square. Therefore, by substituting this E in E place of EF, 2 into r square minus y square, 2 into square root of r square minus y square into dy into y. So like that, we are deriving here. Consider a strip of thickness dy at a distance of y from the neutral axis. Let dA is the area of the strip. dA is the area of the small strip. Then dA is equal to b into dy. The small strip area is, length is b, and dy is the thickness. So is b is, what is the b here? EF. EF into dy. Otherwise 2 times EB into dy. So 2 into EB value is square root of r square minus y square into dy. This is the total equation which represents the area of that small strip. Area of small strip. Next, moment of this area dA about neutral axis. Moment of this area about neutral axis means area into distance of that area from neutral axis. Distance of that area from neutral axis is y. Therefore, dA into y is the first moment of area. So y into 2 into square root of r square minus y square into dy, or 2y into square root of r square minus y square into dy is the first moment of that small area. If we want to get the first moment of area of whole section or whole area above the level EF, whole area above the level EF, then integrate this equation with respect to y. So moment of this whole, moment of the whole shaded area about neutral axis is obtained by integrating the above equation between the limits y and r. Because y becomes y, whenever y becomes y, If we consider the small area, if we consider the small area at this place, the area which is at a distance of y from the neutral axis, the area which small area which is considered at this point, then y becomes r, because from neutral axis the distance is r, radius of the circle. So the for the shaded area, for this shaded area, the distance of small area is varies from y to r. Okay, that's why we are taking the limits from y to r. So by integrating, then we can get the ay bar. Ay bar is the first moment of whole shaded area about neutral axis. In this formula, Fay bar by b into I, in this formula, Ay bar is always represents the first moment of shaded area about neutral axis. Wherever you consider the EF layer, the Ay bar is the total, that is the first moment of area above the EF layer about neutral axis. Here students, always we should consider the layer EF. If we consider the layer EF, Ay bar is the first moment of area above the level EF about neutral axis. Here the shaded area. So Ay bar becomes square integration of y to r, 2y r square root of r square minus y square into dy, multiplied by minus 2 times, then we can it doesn't change the equation, minus into minus plus also. So minus integration of y to r, one of the minus is inside the integration, minus 2y square root of r square minus y square dy. Why we multiplying the minus 2 times? Because the differentiation of square root of r square and the r square minus y square is the differentiation is minus 2y itself. So to integrate or to simplify for that equation, we should multiply the minus 2 times. So now minus 2y is the differential of r square minus y square. Hence the integration of above equation becomes ay bar is equal to minus of, it is having integration of square root of r square minus y square. It is r square minus y square whole power 1 by 2. R square minus y square whole power 1 by 2 integration, r square minus y square whole power 3 by 2 by 3 by 2. It is a mathematical equation. Limits are y r minus 2 by 3. It becomes 2 by 3 whenever we write in the numerator, minus 2 by 3. R square minus r square, when we substitute the r at y plus r upper limit, r square minus r square whole power 3 by 2 minus r square minus y square whole power 3 by 2. Whenever we substitute to y plus y, the equation becomes r square minus y square whole power 3 by 2 itself. So the first term is 0, r square minus r square is 0, minus 2 by 3, 0 minus r square minus y square whole power 3 by 2. Therefore 2 by 3 minus minus plus 2 by 3 r square minus y square whole power 3 by 2. This is the ay bar value itself. Ay bar, the first moment of shaded area about neutral axis is 2 by 3 r square minus y square whole power 3 by 2. So substituting the value of ay bar into our shear stress formula at this place, then we can get the shear stress at that particular level or layer EF. Here ay bar, the formula we derived up to now. Now what is the B value here in this formula? What is the B? B is the breadth of the layer EF. Breadth means distance of EF. Distance of EF is 2 times EB. What is the EB? R square minus y square square root. So 2 into r square minus square root of r square minus y square becomes the breadth of the EF. So in place of B, we can substitute, in place of B equal to EF, that is equal to 2 into EB, 2 into square root of r square minus y square is the B in this formula. So by substituting all the parameters B and first moment of area, shear stress formula becomes, substituting this value of B in the above equation, we get tau equal to F 2 by 3 r square minus y square whole power 3 by 2 by I is the constant, I as it is. In place of B we can write 2 into square root of r square minus y square. So in this equation, by simplifying this equation, 2 cancel. So f by 3i, r square minus y square whole power 3 by 2 by r square minus y square whole power 1 by 2. So it becomes r square minus y square. The students, in the numerator, r square minus y square whole power 3 by 2 is there. But in the denominator, r square minus y square whole power 1 by 2 is there, because square root is 1 by 2. So if we replace this r square minus y square whole power 1 by 2 in the numerator, it becomes 3 by 2 minus 1 by 2. So 3 by 2 minus 1 by 2 is the 1. 3 by 2 minus 1 by 2 is the 1. 2 LCM. 3 minus 2 is the 2. 2 by 2 is the 1. Therefore, r square minus y square is the finally remains the equation. So f by 3i, r square minus y square is the formula to calculate the shear stress at layer EF. Here also the shear stress varies across the section, depends on the y square. So parabolically varies. Shear stress varies across the beam parabolically. That's why I drawn in the earlier slide, the shear stress distribution for the circular section is also parabolic curve. But shear stress at extreme layers, a shear stress at maximum point, how to get these shear stress values? If you substitute y is equal to r, that is y is equal to r means at the extreme layer, or y is equal to minus r means at opposite extreme layer, the bottom extreme layer. So if you substitute y is equal to plus r minus r, then we can get the shear stress values at extreme layers. If you substitute the y in place of y0, y becomes 0 means we suppose to assume the layer EF at a distance at neutral axis. If y is equal to 0, the layer which is considered at neutral axis. If we consider the layer at neutral axis, the y becomes 0. In that case, y0, the maximum stresses will be developed. In this equation, this is the basic equation, f by 3a into r square minus y square. If you substitute in place of y plus r minus r, or plus r square minus r, also r square minus r square is 0. So shear stress values are 0. Shear stress distribution across circular section is parabolic. Also, it is clear from this equation that with the increase of y, the shear stress decreases. At y is equal to r, the shear stress is to equal to 0. Hence, your shear stress will be maximum when y is equal to 0. When y0, shear stress is maximum, that is at a neutral axis. At y is equal to 0, that is at the neutral axis, the shear stress is maximum and is given by. So whenever we substitute the y plus 0, f by 3i into r square is the toe maximum value. So f by 3i into r square becomes the toe maximum shear stress whenever the y 0. But I is equal to pi by 64 d power 4. We know this formula. Moment of inertia of circular section is pi d power 4 by 64. So from that pi by 64, in place of d, you can replace the 2 times r, 2 times the radius whole power 4. From this 2 power 4 is 16, 16 by 64 is 4, pi by 4 r power 4. Pi by 4 r power 4 is the moment of inertia in terms of radius. So by substituting I value at this place, tau max is equal to f r square by 3 into I means pi by 4 r power 4. Okay, so 4f by 3 pi, 4f by 3 pi, f by r square equation becomes f by pi r square. 4 by 3 into f by pi r square. In this equation, pi r square, what is the pi r square? It is the area of circular section. So force by area is the shear stress again. This is called the average shear stress. But average shear stress is tau average equal to shear force by area of circular section, f by pi r square. Then we can replace this equation by tau average. Toe max is equal to 4/3 times the toe average. In previous case, we get the maximum shear stress is 1.5 times the toe average. Toe max is equal to 1.5 times the toe average. In this case, toe maximum in circular section is 4/3 times the toe average. 4/3 means 1.33 approximately. 1.33 times toe average is the maximum shear stress will be developed in the circular section, which is at neutral axis. Okay, these are the two basic sections which are learned in this class. How to derive the equations for the shear stress in the rectangular and circular sections. In the next class, triangular, another basic section, triangular section is there. For the triangular section, how to varies the shear stress variation across the triangular section. So along with this triangular section, we go for some worked examples in the next class. Let us close this class at this point. Bye students. Have a nice time.